of each delta zi. So we choose an element in this universal cover, if you want, such that the sum of adjusted angles, these angles now are real numbers rather than just angles in reals modulo 2 pi, the sum of adjusted angles around any edge of the triangulation is 0. Now, it's not obvious that one can do this, and in fact it takes work to prove that one can do this, but one can do this. That's a theorem that really you have to bore into the combinatorics of triangulations and work fairly hard to prove that this is always possible. So this gives us an element, beta of m, which is in the free Z module generated by this. Well, we have these two versions. Let me actually call this C hat sub 0 and this C hat sub 1. And I want to talk about C hat sub 1 for the moment, the one that allows us arbitrary P's and Q's rather than just odd P's and Q's. Okay? And now then, what you find is that the 5-term relation, there's a very natural lift of it to this covering. You look at the lift, the most obvious lift that you do when your simplices have nice shapes, and then you extend analytically. So I don't want to write down the actual formula because it takes a lot of space, but you just take a nice analytic lift, as it were, of the 5-term relation. The simplest lift that works nicely and discontinuous. Okay? So we'll call this P hat of C. And we have a map from P hat of C to now C wedge C. The original map that went to C star wedge C star, notice that we are now using logs to describe things. So we're now going to C wedge C, and it takes one of these W0, W1s, one of these elements in the universal cover, simply to a very easy formula, W0 wedge W1. And the kernel, I should put a hat on the beta now, beta hat of M, therefore it turns out lives inside of here, and this is what we call the extended block group, beta hat of C. Now, I've pointed out that there are two versions. There's the one associated with this cover, the disconnected cover, and there's one associated to this cover. And using C hat sub 0, you get a slightly different extended block group that in my original paper I called the more extended block group, but which I now call beta hat sub SL of C because of the following two theorems. So we have the following theorem. So I originally proved, this is a theorem of mine, that beta hat PSL of C is exactly the same thing as this H3 of PSL2C made discrete with Z coefficients. And I conjectured at the time that if you use the other version, you replace PSL by SL, and this was proved by Christian Zickert, or rather by Christian Zickert together with Goethe, a German mathematician. So this is Goethe Zickert that the SL version is H3 of SL2C instead of PSL2C, again turned into a discrete group with Z coefficients. Now just a comment. This group clearly maps to this group. If you've got something that only uses even p's, it certainly gives you something here. This is a surjective homomorphism on either side. The kernel here is a Z mod 4. So they don't differ by much. They differ simply by torsion of order 4. So now we have a nice symbolic way of representing elements in this group. And it turns out that the Chega-Chern-Simons class has a beautiful formula in terms of this symbolic way. So let me write this down. So I'd like to describe this in two different ways. I wrote the element. I wrote this lift of my simplex parameter to the universal abelian cover. I described it once as W0 and W1, but remember it was just adjusting angles by P and Q. So I'll use notations either W0, W1, this pair of complex numbers over here, or I'll write Z, P, Q. Okay? So if I know my Z and my P and my Q, I know W0 and W1, and vice versa. If I know W0 and W1, I know Z and P and Q. And now then there's a function called the Rogers dilogarithm, or the extended Rogers dilogarithm. And I'll write it in terms of Z, P, and Q. There's a very nice formula for it discovered by Don Zagier, or suggested by Don Zagier. Don Zagier said it should exist, and then Christian Zickert found the explicit version of it in terms of W0 and W1. But I'll write down the original PQ version. I should use my notes rather than... So this is, again, I use the standard dilogarithm and just adjust it. And the adjustment is a half of log Z plus P pi I times log 1 minus C plus Q pi I minus pi squared over 6. And notice there is not a sign error here. Here you're seeing your W0, but here you're seeing something different from W1. You might have expected a minus sign, log of 1 over 1 minus C. This is not W1 here, and you really have to write this down. It's kind of puzzling and weird that that's the right thing. But it turns out that R gives you a nice analytic map from C hat, so the PSL version, maybe I should have called them C hat PSL and C hat SL. Let me change to doing that, in fact, because it's easier to remember. So this is the disconnected cover, and here we go to C modulo pi squared Z. Or if you only allow even P's and Q's, you actually get a map to C modulo 4 pi squared C. Okay. Now then, our extended block groups, the PSL and SL versions, are defined simply as linear combinations of elements in this cover. So we get maps from the extended block group sub PSL to C modulo pi squared Z, and from extended block mod sub SL to C modulo 4 pi squared c. And this is, in fact, this turns out to be the Chern-Simons class. So this is a nice computation of the Chern-Simons class. So remember, these groups are isomorphic to these homology groups. The Cheeger-Chern-Simons characteristic class is defined on these homology groups. And here is an explicit way of computing it, just using a nice analytic function. So this is now a calculation that Snap can do, that the program Snap can do, or even Snappy can do. No, I guess you need Snap because, no, Snappy can do it. But we do it in Snap. And allows you to compute Chern-Simons invariant. And Chern-Simons invariant was the last ingredient in having something that completely describes the PSL fundamental class. So I should really stop here because I'm out of time, and I wanted to talk about scissors congruence. I think I'll start my lecture tomorrow by talking a little bit about scissors congruence, but let me just give one final theorem. This is a very recent theorem of Zickert's, a very beautiful theorem, in my opinion, which is, it's long been known that there's a connection of these homology groups, of discrete groups, with algebraic K-theory. And algebraic K-theory is, it would take me too long to describe how you compute the algebraic K-theory of a group. But algebraic K-theory is, well, yeah, maybe I won't say more about it, I'll just say the theorem. So it was known that H3 of SL2C made discrete with Z coefficients is the same thing as the algebraic K-theory of C, but the indecomposable elements, K3 indecomposable of C. This was known, and it was known that if you replace C by another field, this was true, but only up to torsion. And the torsion was very mysterious. And what Zickert proves is that K3 indecomposable of any number field is the SL extended block group of the number field. And in particular, the PSL extended block group is therefore just K3 indecomposable, quotiented by a Z4. So this really resolves torsion issues that have been around for several decades. It's a very nice theorem. And one of the reasons it's really nice is because algebraic K-theory satisfies strict Galois descent, which means that if you have a Galois group acting on K and look at the fixed group of it, then K3 of the fixed field, K3 of the fixed field is exactly the fixed points of the Galois group acting on K3. Now a consequence of this by factoring away torsion, you're getting the block group. It tells us that if you take the block group of some field with a Galois action and take the action of the Galois group of K over a smaller group, you get the block group. So that the block group also, you don't quite get this, sorry. What should I say? It at least maps into this. The factoring by torsion turns equality into a possibly just inclusion. Now then, I mentioned that the block element of a manifold sits inside of B of K delta. But there are many different ways of triangulating, or you could actually find other fields that this lives in. And And it's easy to check that if you apply a Galois automorphism of k delta over k, you don't change the block element. So a consequence is of the invariant under the Galois is a proof of something I conjectured many years ago and was able to prove only up to torsion, which is that the block element of a manifold actually lies in the block group of the invariant trace field rather than of a larger field. So a very nice, I've kind of run out of time, so I had a list of problems I wanted to mention, but one nice problem very quickly is it would be very nice to have an explicit way of describing this element. This is a very theoretical way of saying it lies there. We have a very geometric description of the element before we push it down into the invariant trace field. Is there some geometric way of describing this element? Okay, so I'll stop there, and tomorrow I'll start by talking a little bit about scissors congruence before moving on to the topic I planned to talk about tomorrow.